Okay, let's look at this tutorial 4 question. Okay, I have a car headlamp rated at 12 volts and 24 watts is used with a constant 12 volts supply for 1800 seconds. Calculate for the lamp used in this way the following questions. Okay, take note that when you have a lamp that is rated at 12 watts, okay, 12 volts and 24 watts, okay, this 24 watts is the power that you have when you provide it with a 24, when you provide it with a 12 volt source. So essentially what you are saying is that if I connect this 12 volt battery to this headlamp here, okay, and I supply it with a 12 volt source, okay, this battery, this light will give me a 24 watts worth of power. This is what I'm trying to say. Okay, so let's look at the first part. Okay, let's calculate resistance. This is not too difficult. Okay, to calculate resistance, we just need to apply our formula directly. P equals to V squared over R. Okay, submit the relevant values. You have R equals to 12 squared over 24, and you get 6.0 ohms. Okay, for part B, you know that the operation time is 1800 seconds. So it's just applying energy equals to power times time. So you're going to get 24 watts times 1800 seconds. And you end up with 4.32 times 10 power 4 joules. Okay. Okay, number of electrons passing through the lamp. Okay, for this one, since you know the total charge, because you are able to remember the equation is the total energy transferred is equal to the total charge multiplied by potential difference. Okay, so you want to find the total charge, you just take Q equals to W over V, and you get 4.32 times 10 power 4 divided by 12 volts, and you have a total of 3600 coulomb. Okay, but since it's asking for number of electrons, you need to work out how many electrons will give you 3600 coulombs. Okay, and we know that I just need to find n, I'll just take 3600 divided by the charge of electron, which is 1.6 times 10 power negative 19, and I get 2.25 times 10 power 22 electrons. Okay, let's move on to the next part. Okay, now we start to look at this portion. Okay, part B, IV characteristics of the lamp are investigated using the circuit as shown. Okay, so in this case, we have here, this is a variable resistor. Variable resistor. How do I use this? Okay, by moving this jockey up and down, I'm able to reduce the amount of resistor that I have to pass through. Okay, so if I connect this at the lower point, so let's say this is my resistor, I connect it here, I'm tapping this entire amount of resistance. If I connect it right at the top this way, I'm only tapping this small amount of resistance. Okay, so that means this one should be something that's about, because it ranges from 0 to 10 ohms, this should be something close to 0 ohms, and this should be something close to 10 ohms. Okay. Okay, then the next one is just asking for theory. Explain how the resistance of the lamp can be obtained from figure 4.2. This follows from your definition of Ohm's law. So this is purely R equals to V over I. So what I need to do, I'm just taking the ratio of potential difference ratio of potential difference to current. That's it. Okay, nothing special about this. It's just a pure definition question. Okay, let's move on next part. On figure 4.3, sketch the variance in resistance of the lamp when the PD across it is varied over the range of 2 to 10 volts. Numerical values of the resistance are not required. Okay, so how would you expect to draw this? Okay, for this you need to refer to the graph. Okay, and you notice that in the graph you actually have a slight curve. Okay, you can just quickly estimate the values and you end up with your answer to be looking like this. Okay, remember it starts from 2, then it goes all the way up like this over to about 10. It doesn't reach 12. Okay, so let's move on to the last part here. From 0 to 12 volts. Why can't it be at 0? Why can't it be at 12 volts? Okay, let's go back and look at the setup again. Clear this. Let's go to setup. Okay, if you consider the setup here, okay, there's something that is not mentioned here. There's actually a bit of, remember in every circuit, there's always a little bit of internal resistance. Okay, so in this case, if you have some internal resistance here, even if I lower this all the way down to 0 volts, you lower to 0 ohms of EMF, 0 ohms of resistance, what you're going to have is you will have a circuit that looks like this. Okay, I'm just going to draw one cell. Okay, and then you have your lamp here. Okay, this, when you have such a scenario, the potential difference across your bulb will never be 0, simply because to find this PD, I do VR equals to R over R plus R, and this cannot be equals to, and this cannot be equals to 12. It will always be less than 12. Sorry, multiplied by my EMF of 12. So this will always be less than 12. Okay. It will always be less than 12. Okay. Okay. Again, then now let's look at what happens on the other end. Clear the screen first. Okay. Okay, so let's say I lower this all the way down to the maximum here. Okay, when I do this, I will have a maximum resistance of 10 ohms. This one has a maximum resistance of 6 ohms. Okay, so if that happens, and let's say you have some internal resistance here as well, your V across your bulb, okay, it will be 6 over 6 plus 10 plus R, and again it cannot be smaller, it cannot be 0. Okay, so you explain why it cannot be at 12 exactly and why it cannot be at 0 exactly. Okay, so this is it for question 4. Let's look at question 5 now. Okay, oops. Okay, I have a battery of EMF E and internal resistance R connected to a variable external resistor capital R as shown. When capital R is 16 ohms, the current is found to be 0.45 ampere. Okay, the current switch on for 1000 seconds, and during this time, the battery supplies 4050 joules of energy to the two resistors. Calculate the charge in which the battery delivers in 1000 seconds. Calculate the EMF of the battery, the PD across PQ, the terminals of the battery, and the internal resistance of the battery. Okay, so when I set this up, let's set this up to be 16 ohms. It should be 16 ohms. Current is 0.45 amperes. Okay, I switch this on for 1000 seconds and I supply 40-50 joules of energy in the system. Calculate the charge in which the battery delivers. Okay, this one is purely just take charge equals to current times time. So it is 0.45 multiplied by 1000 seconds and you get 450 coulombs. Okay, EMF E of the battery, again straightforward because we know the energy and we know the charge and we know that work done is equals to Q total charge multiplied by potential difference. So your V is equals to work energy transfer over charge. So your work done is 4050 divided by charge of 450 and you get 9.0 volts. Okay, so this is the EMF of the battery. Okay, potential difference across PQ. In this case, we need to take into account, okay, this is still quite straightforward because I know this current going through here is 0.45 ampere, okay, and it goes through a resistance of 16 ohms. So how much do I need to push it? Okay, I just need to define my VPQ. Okay, VPQ is basically the current going through PQ and the resistance of PQ. Okay, so this will be 0.45 times 16 and I get 7.2 volts. Okay, internal resistance R of the battery. Okay, take note that this internal resistance and this 16 ohms resistor, they are in series. Okay, so this makes it very convenient for us. We can just apply our potential divider equation. So VPQ is basically the ratio of capital R over capital R plus small r multiplied by EMF. So I submit the values. This will be 16 plus R multiplied by 9.0 and this should give me 7.2. Okay, and in this case your R will correspond to 4.0 ohms. Okay, if you're not sure how this working is done, you just need to shift this one over and then just apply across your cross multiplication. So this is it for question 5. Let's clear the screen and let's move on to question 6. Okay, coil of 1500 turns of insulated wire is tightly wound on a non-magnetic tube to make a solenoid of mean radius 22 mm as shown in the diagram below. Wire has a radius of 0.86 mm and is made of a material of resistivity 1.7 times 10 power negative 8 meters. Coil is connected to a supply of EMF 12 volts and negligible internal resistance. Okay, so how long is the wire? Okay, basically, to find out the length of the wire, you have to consider how many loops are there. In this case, there's 1500 loops. Okay, to make a solenoid. A solenoid is basically a long coil of wire. Okay, you have multiple coils together. Usually, you wrap it around a tube to keep the shape stable. Okay, 22 mm. So if you can work out what is the circumference of the tube, okay, by multiplying this with 2 pi r. Okay, I can easily work out the circumference by C equals to 2 pi r, and r is equals to this 22 mm here. And then to find the total length, I just take the number of loops multiplied by your circumference. Okay, so to find this total length of the wire, I just need to submit the values. So this would be 1500 multiplied by 2 pi 22 mm. So this will be 22 times 10 power negative 3. Okay, so this is square brackets. Okay, and you should get an answer of 207 meters, which is quite long. Okay, once you have this, you can work out the total resistance. Okay, what do I need to find total resistance? Okay, let's use the next page to have more space. Okay, how do you find total resistance now? Since the length of your cable is equals to 207 meters, okay, how about the cross-sectional area? Okay, you are given the cross-sectional area as pi r squared. In this case, the r is not the same r just now. This will be pi 0.86 millimeters, so times 10 negative 3 square. Okay, so what you want to find resistance, you are looking at R equals to rho L over A. Sub in the values. So your rho is 1.7 times 10 power negative 8. L is 207 meters. And then you divide this by pi 0.86 times 10 power negative 3 squared. And your final answer should be about 1.51 ohms. Okay, after this you're asked to find current. Okay, nothing too difficult. It's just I equals to E over R. So you have 12 volts divided by 1.51. You get something close to 7.95 amperes. Okay, not much difficulty. Okay, question 7 we'll skip. Question 7 is purely definition. You can refer to your notes, nothing too difficult about it. There's quite a bit of explanation which I'll leave you to find on your own. Let's jump on to question 8. Okay, question 8, I have a filament lamp rated at 240 volts and 60 watts. Calculate the current through the lamp when it's working normally, resistance of the lamp when it's working normally, etc. etc. Okay, what does it mean for the lamp to be working normally? Okay, when you want the lamp to work normally, if it's marked as 240 volts, it means that you need to supply 240 volts. Okay, it doesn't mean that when you supply less than 240 volts, let's say you supply 100 volts, the lamp will not work. The lamp will work, as you've seen in the practical that we just did. When you use a smaller potential difference, the lamp will not glow as bright. Okay, this is because of the power. We'll show you how to do it later. Okay, current through the lamp when it's working normally. So this is just I equals to P over V. So this is 60 over 240. I get 0.25 amperes. Okay, resistance of lamp is working normally. R equals to V over I. So V is equals to 240, resistance of, current of 0.25, and I get 960 ohms. Okay, let's look at this number. Let's see what happens when the lamp is not working normally. If, let's say, I give it a potential difference of 100 volts now, the new power would be V square over R, and this would be 100 square over 960, and you should get a number that is less than 60 watts. Okay, similarly, if I give it a larger power, larger potential difference, let's say V equals to 300 watts. Okay, and again I do P equals to 300 volts, I mean. So raise this, let's make it a bit more correct. 300 volts. Okay, so 300 square over 960. Again, I'll get a value that's larger than 60 watts. Okay, what are the risks in doing this? Okay, if you run it at a lower potential difference, your bulb won't be so bright. Okay, and if you run it at higher potential difference, the bulb will be brighter. Of course, this will bring it into the risk of burning out, like we saw just now. Okay. Resistance of lamp is found to be less when it's not lit, when it's working normally. That was when it's working normally. Sketch the current, voltage, characteristics of the filament lamp as shown. Okay, remember in this case, you are supposed Okay, so you draw up to 240 volts. At 240 volts, you know that your current is at 0.25 amperes. 0.25 is somewhere here. Okay, so you know that your value should not go higher than this. You should end somewhere here. Okay, remember when you have a higher temperature, your resistance will be higher. So the graph will not be a straight line all the way to here. It wouldn't be something like this. This is wrong. Okay, so how will it look like that? Okay, how will it look like that? Okay, if my resistance is increasing, that means my potential difference should be increasing faster than my current. So the curve should look something, it should be steep at the start. Okay, it should be steep at the start before it gradually evens out to somewhere here. This is your answer for this part. Okay, so we're done with question 8 as well. Let's move on to question 9. Battery has an EMF of 12 volts and negligible internal resistance. A resistor of resistance 3 ohms is permanently connected to one of its terminals. Okay, this battery and resistor form a power supply terminals X and Y as shown in figure 9.1. Okay, so effectively you put this one here and then you connect it permanently. That means right now you are locking this up. Okay, so effectively this 3 ohm resistor is functioning as your something like an internal resistance. Okay, so now I connect a variable resistor across X and Y. Okay, so I want to find out what's the maximum possible current from the supply. Okay, maximum possible current. Okay, I know that I is equals to total EMF divided by total resistance. And total resistance will be equals to 3 ohms plus whatever that's outside here, this R. Okay, so if I want to maximize this, I let R be equals to 0. If R equals to 0, my I will be equals to 12.0 divided by 3 plus 0. So I have 4.0 amperes. Okay, maximum safe power rating of the 3 ohm resistor. Okay, this is asking for how much power must it be able to withstand. Okay, to find how much power it needs to be able to withstand, I just look at what's the maximum possible current. The maximum possible current will be here when this R is equal to 0. Okay, so it's just quite straightforward. I'll be just applying P equals to I square R. Okay, and this will be the maximum current from here. So 4.0 square times resistance 3.0. So I have 16 times 3, so I have 48 volts. Okay, last part. Suggest the purpose of the 3 ohm resistor. What do you think this 3 ohm resistor is supposed to do? Okay, if you don't have this 3 ohm resistor here over here, let's say you remove it, so this one becomes, let's say now this one becomes 0 ohms. Okay, there will be no issue if this R is not equal to 0. Okay, but if your R tends to 0, that means now your total current will be 12 over R, and if R tends to 0, my I will be almost like 12 over 0, which will give me a very large value, close to infinity. Okay, so basically this one here, this 3 ohm resistor here, is acting to protect the circuit, especially the battery here. Because if you don't have this 3 ohm resistor and you set this resistance to be very, very low, what you're gonna have ending up here is that you will have a short circuit. Okay, and you don't want that to happen. Okay, and that's about it. Okay, let's continue for the last part over here. Okay, how resistance R is varied. Okay, so this is from the previous question over here. This resistance R can be varied from 0 to close to 0 to about 15 ohms or so. Okay, and then what we do is that we measure the power dissipated across it. Okay, so how do we measure this? You can just simply tap a voltmeter across it and then or work out the current. If I were to find the current, then you can calculate how much of the power dissipated across this. Okay, so state the two values of R at which the power dissipated in the variable resistor is 9 watts. Okay, so this is quite straightforward. I just need to look for 9 and I realize that it intersects here. Okay, oops, sorry. So it's at 9, so let's just mark this out over here. This is roughly about 1 ohm, and then the other time it intersects is about 9 ohms. Okay, so these are the two values at 1 and 9. Calculate the efficiency of transfer of power. Okay, efficiency of power, what I'm trying to see is that this. I want to find out what is the ratio of the power output from here. I want to find out what is this power output. Okay, to how much is being supplied by this cell. How much power is this battery providing? So this is my input power basically. Input to the whole circuit. Okay, remember this is acting like internal resistance, so only concerned about power output from here. Okay, let's go back to this one over here. Okay, if I have my circuit, okay, I want to find the power supplied first for each one. So when it's at 1 ohm, okay, now your total resistance is basically 1 plus the original 3 ohm. Okay, so what I have is total of 4.0 ohms of resistance, and my current will be 12 over 4.0, and I get 3.0 ampere of current. Okay, multiply, if you want to find the total power supplied, will be P equals to IV. In this case, this will be 3.0 multiplied by 12 volts. This is your EMF, and you get 36 watts. Okay, so now your efficiency will be power output here is 9 watts, so 9 over 36 times 100%, and you get 25% efficiency. Okay, now doing the same for the 9 ohms, your total resistance, let's change the color for the pen. Let's see, let's go for red color. Okay, so now with 9 ohms, your new R is equals to 1.0 plus 9.0. I have 10.0 ohms of resistance. The new current will be 12 over 10.0. I get 1.2 ampere. The new power developed by the cell now will be 1.2 multiplied by 12.0. Okay, so I'll get, sorry, this is 1.0, sorry, this is plus 3.0. This is plus 3.0, so you have 12 ohms of, you have about, so this one should be changing this as well, and this one as well. Okay, so this is 12 ohms, so this is divided by 12, and I get 1.0 ampere, and 1.0 times 12. So the power developed is 12 watts. Now the effective power output is 9. As seen from here, your new efficiency is now 9 divided by 12 times 100%, and I'll get 75%. Okay, so obviously this 25% compared to this 75%, you have less power wastage in the 75%. Okay, this is much more efficient. You are generating power, both in the first case, you're generating more power from the cell, but only 9 watts is used, 25% is used. In the second case, you're only generating 12 watts, but you're using 9 watts usefully. So you're making full use of 75% of it. Okay, so let's look at this one over here. Okay, a battery is designed to provide the power for a component that has a fixed resistance. Okay, internal resistance R of the battery is chosen to provide maximum efficiency of energy transfer to the component. Use your answers in B. Explain the choice of R compared with the component's fixed resistance. Okay. So when I design a circuit like this, let's just draw a simple mock-up of a circuit. Okay. Okay, so let's say this has internal resistance. Okay, this is small r, this is capital R. Remember, this one is enclosed, treat that as 1. Okay, if I want to maximize, if I want to make full use, increase the efficiency, right, I want PR, power distributed across R, versus the power developed by the cell to be as close to 1 as possible. Okay, in order, and this one, this is given by total current. Okay, so what I can see is that I can actually work out what is the total power developed. This is just equals to total current multiplied by your EMF. Okay, in this case, this PR is I VR. Okay, so it cancels off to VR over E. And VR, using a potential divider concept, is basically your EMF times your R, capital R, over capital R plus small r divided by E again. Okay, I can make the necessary cancellation. Okay, so in order for this to be maximized as close to 1 as possible, what should I do? Okay. So you should have a scenario, if you are able to reduce your R, if your R tends to 0, your whole relationship will be R plus small r. Okay, and this will give you, okay, and this will be almost 1. Okay, so what I'll do is that you want to make sure that your choice of internal resistance, this extra resistor here, is as small as you can compared to this one. Okay, so in order for you to maximize your power, this one should be as small as possible to your external load, or make your external load as large as possible compared to your small r.